This is going to be a bit more, I'd say, um, thinking about and investigating a bit more about the quantum volume thing here, because I came across this concept when I was taking a look uh, at one of the papers from Rod that's using the NISQ for quantum computers thing. Can I not find the paper? Grover for NISQ or something like this. Yeah. So in this paper, they extensively talk about it, but also quantum volume. I think in the Kiski textbook, there's also a whole chapter about it, which I haven't covered yet. But we might as well do it now. The point for me doing this is that I see there's a bit of a so the IBM clearly uses these as a marketing thing, where marketing or maybe a way to communicate. It's a single number metric that can be measured using a concrete protocol on near-term quantum computers of modest size. The QV method quantifies the largest random circuit of equal width and depth that the computer successfully implements. Quantum computing systems with high fidelity operations, high connectivity, large calibrated gate sets, and circuit rewriting tool chains are expected to have higher quantum volumes. But there seems to be, so here there's also going to be, I think, a bunch of, volume. Quantum volume as a quantitative indicator of the computing power of quantum processors. And that's, okay, so this is is this the sort of the original paper where this is proposed, or? Is this one the paper? Then there's the stuff from quantum. There's the take from Quantum Computing Report, which I haven't read yet, but I can quickly scan. And this also, this is the reason I decided to do this video is because I saw today a tweet from Craig where he doesn't tweet often, and he works at Google, but he seems to make fun of this. The best quantum volume announcement is typical of NISQ news in that it ignores the real competition. Remember, a PC with a fast state vector simulator easily has a quantum volume of 7 billion. Supercomputers with specialized simulators get into the quadrillions. Also, an argument for reporting log to QV like God intended. Yeah, it's very strange that they drive it that way, presumably to make it sound more impressive. Log quantum volume, more like you, for sure. It's clearly better for a technical person standpoint. Let's try to understand a bit more of these first, and then let's see, and let's try to take a look at different perspectives on this issue. It's just a number, really. But I guess it gets tricky when you think about, okay, should we use this number to measure how powerful a computer is, right? And that's where the number should make sense. So let's take a look at what IBM, which seem to be the ones that propose these, right? Because this is all. So Jay Gambetta is basically from IBM. So and this is the paper. Okay. But the paper is maybe worth reading also. What's the abstract saying? The concept of quantum computing has inspired a whole new generation of scientists, including physicists, engineers, and fundamentally changed the landscape of information technology. With experimental demonstrations stretching back for more than 2 decades, the quantum computing community has achieved a major milestone over the past few years: the ability to build systems that are stretching the limits of what can be classically simulated and which enable cloud-based research for a wide range of scientists. This increases the pool of talent exploring early quantum systems. While such noisy the bright unique test beds for exploring the opportunities of quantum applications. Here we highlight the facilitated systems, including quantum software, cloud access, benchmarking quantum systems. Okay, so this is more than that, but then there's a chapter in benchmarking quantum systems, and I'm assuming this is going to be there. Benchmarking systems. Okay, benchmarking near-term devices. I see connectivity, error rates, gate set, compilers and software stack performance, quantum volume. IBM has devised a benchmark called quantum volume that balances all of the ingredients above. Okay, so this is not pitched in here. Originally, it's pitched in here. We believe this system-agnostic metric provides a way to compare devices across different physical implementations and measure qualities such as lower error rates that are ultimately necessary for a practical quantum computer. Validating quantum computers using randomized model circuits. Okay, that's the actual paper. That's the one I won. Algorithm, okay. So it's about 5 pages. So anyway, let's take a look at the, I feel like we can start here probably. Good. Quantum volume is a single number metric that can be measured using a concrete protocol on near-term quantum computers. I read that. So what's the quantum volume protocol? A QV protocol, C1, consists of the following steps. We should first import the relevant Qiskit classes for the demonstration. The QV function generates QV sequences. It is well known that quantum algorithms can be expressed as polynomial-sized quantum circuits built from 2-qubit unitary gates. Therefore, a model circuit consists of d layers of random permutations of the qubit labels followed by random 2-qubit gates from SU4. When the circuit with M is odd, one of the qubits is idle in each layer. More precisely, a QV circuit with depth D and width M is a sequence of D layers of U's, each labeled by times T equals 1 to D and acting on M prima qubits. Each layer is specified by choosing a uniformly random permutation of the M qubit indices and sampling each acting on qubits A and B from the Haar measure on, what the hell am I reading? In the following example, we have 6 qubits, Q0, 1, 3, 5, 7, 10. We're going to look at subsets up to the full set. Each volume circuit will be depth equal to the number of, so we're going to take a look at the odd subsets up to the full set. Each volume circuit will be depth equal to the number of qubits in the subset. We generate the quantum volume sequences. We start with a with a small example, so it doesn't take too long to run. As an example, we print the circuit corresponding to the first qubit sequence. Note that the ideal circuits are run on the first n qubits. No. Pass the first trial of the transpiler to illustrate the circuit. Basis gates U1, U2, U3, and CX. So that's a... So there's a bunch of U3s, control nodes, U3s, control nodes. Simulate the ideal QV circuit, step 2. So you're coming out with a circuit that is basically... What I think they are going to is that with these control gates in here, they basically, you can only do that if there's connectivity. So I'd say if you cannot place an operation, then you're going to have a lower quantum volume. Then you simulate the ideal QB circuits. Then you calculate the heavy outputs. Maybe what they mean by this is the actual outputs. To define when a model circuit U has been successfully implemented in practice, we use the heavy output generation problem. The ideal output distribution is this, where it's an observable bit string. Consider the set of output probabilities given by the range sorted in ascending order. The median of the set of probabilities is this, and the heavy outputs are X belong to this set such that, okay. So the heavy outputs are the outputs that are over the medium, the median probability, right? So they are the heavy ones in the interesting. The heavy output generation problem is to produce a set of output strings such that more than 2/3 are heavy. We print heavy outputs from various depths and their probabilities. So for qubit least and qubit least, okay, so define the noise model. Okay, but this is then okay, define the noise model. We define the noise model for the simulator to simulate decay. We add the polarizing error probabilities to the CNOT and U gates. We can execute the QV sequences either using Qiskit, the AI simulator, or an IBM Q provided to obtain a list of experimental results. Calculate the average gate fidelity. The average gate fidelity between the M-qubit ideal unitaries U and the executed U prima. The observed distribution for implementation. And the probability of sampling a heavy output is this. As an illustration, we print the heavy output counts from various depths. Calculate the achievable depth. The probability of observing a heavy output by implementing a randomly selected depth D model is these. The achievable depth is the largest D such that we are confident. We now convert the heavy outputs into different trials and calculate the mean quantum volume for up to 6 qubits and 50 trials. With a qubit subset. Okay. The quantum volume is the width and the depth of the model circuit with equal importance and measures the largest square-shaped model circuit a quantum computer can implement successfully on average. The quantum volume is defined as log 2. So here's the log 2 though. argmax, mean. We'll list the statistics for each depth. For each depth, we'll list if the depth was successful or not, and with what confidence interval. For a depth to be successful, the confidence interval must be over 97.5%. With depth 3 greater than 2/3, with confidence 0.99 successful. Quantum volume is 8, I guess 2 to the power 3. Okay. So they basically, with depth 3, this means that they are generating 3x3 circuits. If I understood all this blah blah here well, what does it mean? What is a QV sequence? Pum 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 pum. This polynomial size quantum circuits built from 2 qubit unitary gates. A model circuit consists of d layers of random permutations of the qubit labels. A model circuit consists of d layers of random permutations of the qubit labels, followed by random 2 qubit gates. What is SU for? What is this? When the circuit with the M is odd, one of the qubits is idle and each layer doesn't, whatever, I don't care. More precisely, a qubit circuit with depth D and with M is a sequence of the unitary gates, UD, of D layers. Okay, so each of these is a layer, and then each layer is U labeled by times T and acting on M qubits. Each layer is specified by choosing a uniformly random permutation. A uniformly random permutation. Random permutation. So that's a random permutation of the M qubit indices, and sampling each. This is it feels a bit dense. UAB prime T acting on qubits A and B from the Haar measure on SU4. What is this? So, but basically what this is doing is you're giving it a list of qubits, and then it's telling you to create a 50 qubit circuits, 50 model circuits for each of these subsets of qubits. That's what this thing does. And what? And so this is one of the circuits. Why does one qubit stay idle? Because M is odd. That's what they said here, right? On the circuit with so we in this case they define width as in like vertically, so the amount of qubits, and depth is like how far it goes. I think so, right? So that's depth and that's width. Okay. I think that's one of you says it'll need a layer. Okay. Okay, I guess the idea is odd is because then you cannot fill in all the stuff with so you're gonna have to have one because you have like 2 qubit gates, like control nodes, and so you don't want to basically, for some reason, you want to avoid, or you don't want to allow these for some reason. I don't know why though. Then the whole idea is you simulate those. You simulate those, and then okay, so then there's this whole thing with the heavy outputs in here. Wrote the ideal results into a quantum volume feeder. What is distinct with the heavy output? So define when a model circuit U has been successfully implemented in practice, we use the heavy output generation problem. The ideal output distribution as an observable bits. Okay, so it's considered a set of output probabilities given by the range Pu x sorted in ascending order. The median of the set of probabilities. So the heavy outputs are, and they are the ones that have probability higher than the median. The heavy output generation problem is to produce a set of output strings that more than two-thirds are heavy. Okay. Why though? As an illustration, we'll print the heavy outputs from various depths in their probabilities for trial 0. QFIT heavy output probability ideal. Okay. I'm not sure I grasp that completely. The heavy outputs thing. But basically, it's a measure of how well does this really. I think it's basically, it's trying to be permissive, right? In terms of you want to sample the circuit, you want to sample the actual results and then compare them to the ideal results, but you don't want to be too picky, so because of errors and whatnot. So what you do is you take the heavy outputs and then what? Gate fidelity. Why are we now calculating gate fidelity? Achievable depth. We now convert the heavy outputs into different trials and calculate their mean and the error for plotting the graph. And so the quantum volume is defined as the width, the largest square-shaped model circuit a quantum computer can implement successfully on average. And that average success is if the confidence, or if that the experimental results of that qubit match the ideal results with 97.5% confidence at least. But that matching is done with the heavy, what do they call the heavy, what? The heavy outputs. Okay. That's still a bit confusing, but let's see. Let's see what quantum computing report has to say. The metric quantum volume has been in the news lately, and this is a few more words of explanation. This metric was first created by IBM in 2017 and modified in 2018 as a metric that would allow comparison of different quantum computers. It has many valuable characteristics. It is a well-documented, straightforward way of comparing different quantum computers that can be run on any gate-level quantum computer, not just ones that use superconducting technology. Most importantly, it considers qubit count, qubit quality, and other factors, so it does not emphasize the number of qubits alone. It is a good tool for use by quantum hardware engineers to measure their progress in development. If they are able to come up with a new generation of hardware that increases this metric, they are going in the right direction. However, it is a poor tool. It is a poor tool for end users to use if they want to measure the goodness of a quantum computer for solving their computational problems. Okay, seems like I think I kind of agree. I mean, that takes what's obvious to me is that this takes into account, but it does not really take into account connectivity, does it? Because all honestly, if you cannot connect, like how is quantum volume taking into consideration connectivity, for example? Because they clearly said that in here, right? No, not in here. In the previous paper. So I was coming from here, and they basically benchmarking, they said it takes into account the number of qubits. Of course, because the more qubits, the bigger the depth and the width. Connectivity. How qubits are connected to one another matters. At one extreme, qubits connected on a line would require significant overhead for any randomly selected gate between any random pair of qubits. At the other extreme, if all qubits are connected to each other, there is no additional overhead for a randomly selected gate between any random qubit pair. However, at the hardware level, connectivity matters a lot and greatly influences metrics such as crosstalk, fidelity, etc. It's important to strike a balance between connectivity and overhead for a given application. But I don't really see directly how is that included in the metric. Error rates, obviously, because if the qubits are prone to errors, then you're not gonna get successfully implemented circuits. Gate set, the choice of and performance of the underlying gate is important. A large set of gates reduces the overhead to synthesize arbitrary gates or move quantum information, but also requires far more complexity for calibration and stability. But that's the same like error rates, right? This means if your gate set is really broad, then you better be good at implementing those things and controlling those things. If your gate set is small, then it means that for certain operations, you're gonna have to basically combine a lot of other gates to create and synthesize another gate, which this means you've got a chance of piling up errors. Compilers and software stack performance. How is that even considered in there? All of the ingredients above. Compilers and software stack performance. How is that included in there? Honestly, it's not obvious to me, but maybe anyway. But I agree, it's not about how good the quantum computer will help you solve the problem. It's like with this paper here, right? So can I see the volumes? Ourense volume 8, Valencia volume 16, right? And so I don't see any, like, this is a volume that's twice the it's twice for Valencia, right? But if you take a look at these results and take a look at the dark blue versus the light blue, right? So here you've got Valencia and Orense, and the results are pretty similar, to be honest. Here you've got an exception, but it's not a solution to the problem anyway. Here as well, I guess I chose the wrong color. Here I've got a difference. Here I've got a little bit of a difference. Or here I've got a big difference. But it's not like, in general, the whole distribution in here, and also even this case, which is, you've got another a bit of a different gate set, the art of M and the art of IX. They don't, like, it's not, you can't see a big difference between these two processors, and they've got I would say a significantly different quantum volume. So that seems to be a good point. We will explain. Okay, so the goodness of a quantum computer for solving their quantum. Yeah, I hope I haven't said something stupid, but it seems like this is it, right? KL divergence. We'll explain why quantum volume is not really appropriate for end users in this brief. But first, we'll provide a simplified explanation of how this measure is derived. The quantum volume measurement involves testing a series of circuits with a square configuration. By that, we mean that the number of qubits equals the gate depth of the circuit. For example, a test may begin by trying out a 2x2 configuration. This would mean a 2-qubit circuit with each gate going through 2 gate levels. In these tests, the gate sequences are alternating sequences of single qubit gates followed by 2-qubit gates. The circuit is run multiple times with the results measured, and the results are analyzed with a certain statistical test to see how accurate the answer is to what would be the theoretical result. Okay, that's the heavyweights thing. If the test passes a certain criteria, then the test is repeated for a 3x3 configuration, 4x4 configuration, etc. Because qubits are imperfect, each increased level gets harder and harder because the gate errors are stacking up and the test no longer passes the criteria. Once a larger square array is found that will pass the test, the quantum volume is calculated as 2 to the power of n, where n is the number of qubits and gate depth. So a 4x4 circuit would have a quantum volume of 16, a 5x5 circuit of 32, a 6x6 of 64, etc. For complete details on how this test is concluded, we refer to you to the paper that the IBM posted on arXiv. Okay, but that's basically, that matches my understanding of these, I'd say, at the intuitive level. I do see here, I do ask myself probably, or I see sense in the question of why log 2 is what we're taking a look at. If you're calculating 2 to the power of n, it's weird. Or I'm not so sure I understand. Okay. But it's it's maybe a useful measure, as in, like, to kind of quantify the errors, or to quantify how good a quantum computer is. But honestly, if the quantum computer would have almost no errors, then that shouldn't be a factor. Okay, but then you've got connectivity. You've got a bunch of other factors they talked about here, connectivity and gate set. But again, I don't see how connectivity is tested in here. The gate set, compilers. The gate set maybe makes sense, right? The gate set kind of makes sense. Here are concerns about quantum volume. Okay. The test is all based upon a square circuit configuration, but very few quantum programs really have a square configuration. Some of the algorithms being developed for NIST computers such as VQE and QAOA are wide and shallow. This means that they use a larger number of qubits but only a few levels of gate depth, or others may have much larger number of gate operations versus the number of qubits. For example, Shor's algorithm can theoretically factor 2048-bit numbers using about 4,100 logical qubits, but it requires about 8.6 times 10 to the power of 9 gate operations. Note that this is based upon logical or error-free qubits and not physical qubits. This is all based upon a square circuit. Yeah, so we do not agree with calculating the quantum volume by using a formula of 2 to the power of n. We think this gives a distorted view of how fast the quantum computer performance is increasing. Let us explain this by an analogy. Let's suppose we are looking for office space and the landlord shows us two office spaces with this office space with I mentioned 5 by 5 or 6 by 6. You can use either feet or meters as the dimensions depending upon what country you're in. Would you expect to pay twice as much for 6 by 6 as for 5 by 5? No, you could calculate the worth by looking at the square area and determine the 6 by 6 is about 44% more valuable than a 5 by 5, not 100%. In a quantum computing algorithm, we do not think an end user would be able to increase their problem size by 100% if they were provided a new quantum computer that just had one more qubit and one more gate level. Okay. Yeah. But I mean, that's a question of how you sell these, right? Like the arguments here so far don't seem so much about the metric itself, but about how it's used. The focus for anyone developing a quantum computer should be how to make it achieve quantum advantage and solve problems better than a classical computer. Since classical computers are error-free, the equivalent quantum volume for a quantum program running on a quantum simulator on a classical computer can be very high. For example, in 2019, Google ran a quantum benchmark on the Summit supercomputer that successfully calculated the results of a 49 by 40 circuit. So the equivalent QV for Summit would be to the power of 40, or okay, that's the same point that Craig makes in here. So, I mean, I agree with these, but I don't know where the critique is coming from, though. As in, like, is it that, I don't know. I get it. It's like it's not, it doesn't necessarily mean your quantum computer or your QPU is better than another one with a lower quantum volume. I think this is probably my personal opinion here would be that that's a metric that one can use to measure progress within your own development, right? So if the volume increases, it's kind of what they say here. It means you're going in the right direction. But to compare quantum volumes even between QPUs from different companies, it doesn't make much sense either, because it depends. It depends on. I don't know. It feels. It feels awkward. It doesn't feel like it makes a lot of sense, but so this is the permutation. So this is a model circuit. Okay, so this is the original paper, validating quantum computers using randomized model circuits. Single number metric quantum that can be measured using a group protocol. Yeah, the point is you cannot, like, the thing is, once you reach numbers that go over like the 50, 60, 70 threshold, like, then you won't be able to run that anymore. So what's the point? Like, what's the point of that? Is it supposed to mark the path towards? I don't know. I don't know. A model set consists of d layers of random permutations of the qubit labels, followed by random 2 qubit gates. Okay, so these are the 2 qubit gates here, and this is the random permutations of the different qubit levels. This means probably the different gates you wanna. Yeah, that's even. I mean, that's even the. It's the point in here. Is like if you're gonna measure, like if you know, a quantum computer at IBM can have the base gates say U1, U2, U3, and control knot, while another one will have another set of base gates. Yeah, okay, but I get it. Yeah, you do that, and then you still can. It doesn't. Okay, so it doesn't really matter. That's the point of the measure. If you're able to pull off a square circuit that's big enough, then it means your quantum computing approach is, or your QPU rocks, right? That's the idea. But I don't know. I really. Here as a good example, like there's just a jump from 8 to 16, and there's no visible improvement in how the circuit runs. This is the first thing that I can see here of how well the circuit runs. These points in here don't seem super strong. I get it, the one with the simulation makes sense, but that's the point. The point is just to measure NISQ computers, right? So that's why I find this a bit, yeah. It's like, yeah, there's a point in that. There's a point in that, but I guess IBM people have a point as well when they say, I mean, I don't know if they say that, but I guess that's the point is you want to try to measure in that direction, right? So are we getting better than the simulators? But you won't get better than the simulator, right? Because the simulator is really just error-free. So it's kind of limited by, and you need the simulator to calculate the quantum volume anyway. I'm not so sure whether I should like it or not like it, to be honest. Quantum volume. Oh, let's see. Let's see Scott Aronsson's take on this. Ooh, okay, cool. So several people asked me to comment on the recent announcement by Honeywell that they'll be. Oh, that's a pretty fresh post, I guess. That they'll soon have what they call the most powerful quantum computer. I'm glad that Honeywell, which many people might know as an air conditioner manufacturer, has entered the race for trapped ion quantum computing. I wish them success. I've known about what they were doing in part because Drew Potter, my friend and colleague at UT Austin's physics department, took 1 year leave from UT to contribute to their effort. Here, I wanted to comment about one detail in Honeywell's announcement, namely the huge emphasis on quantum volume as a central metric for judging quantum computing progress and the basis for calling their own planned device the most powerful. Okay, so they basically use the quantum volume to then say that's going to be the most powerful quantum computing to date. One journalist asked me to explain why quantum volume is such an important measure. I had to give her an honest answer. I don't know whether it is. Yeah, I kind of feel like the same. I really don't know. I can't. Can I undo retweet? Yeah. I don't know really. Was invented a few years ago by a group at IBM. According to one of their papers, it can be defined roughly as 2 to the power of k, where k is the largest number such that you can run a k-QE random circuit with depth k and with any-to-any connectivity and have at least, say, two-thirds probabilities of measuring an answer that passes some statistical test. In the paper, they use what the G, Chen, and I named heavy output generation. So that's from Scott. Okay. Though Google's linear cross-entropy benchmark is similar, I don't know why IBM takes the volume to be 2 to the power of k rather than k itself. Leaving that aside, though the idea was to invent a single goodness measure for quantum computers that can't be gamed either by building a huge number of qubits that don't maintain nearly enough coherence, what one might call the D-wave approach, or by building just one perfect qubit, or by building qubits that behave well in isolation but don't interact easily. Note that the any-to-any connectivity requirement makes things harder for architectures with nearest neighbor interactions, only like the 2D superconducting chips being built by Google, Rigetti, and IBM itself. You know the notion of a researcher's H index, defined as the largest H such that she's published H papers that garnered H citations each? I didn't know what this. Quantum volume is basically an H index for quantum computers. It's an attempt to take several different yardsticks of experimental progress, non terribly useful in isolation, and combine them into one consumer index. Yeah. Certainly, I sympathize with the goal of broadening people's focus beyond the "but how many qubits does he have?" question. Since the answer to that question is meaningless without further information, from that standpoint, quantum seems like a clear step in the right direction. Alice Goodhart's law states that as soon as a measure becomes a target, it ceases to be a good measure. Yeah, that happened years ago with the H index, which now regularly pollutes academic hiring and promotion decisions. Quantum volume is now looking to me like another example of Goodhart's law at work. The position of Honeywell's PR seems to be that if they can build a device that can apply 6 layers of gates to 6 qubits with full connectivity and good fidelity, that will then count as the world's most powerful quantum computer, since it will have the largest volume. One problem here is that such a device could be simulated by maintaining a vector of only 64 amplitudes. This is nowhere near quantum supremacy, beating classical computers at some well-defined task, which is necessary, though not sufficient condition for doing anything useful. Okay. So think of a university that achieves an average faculty-student ratio of infinity by holding one class with 0 students. It gets the best score only by exploiting the opposite effect in the scoring system. So what's the alternative? The policy I prefer is simply to tell the world all your system specs as clearly as you can, with no attempts made to bury the lead. How many qubits do you have? With what coherence times? With connectivity? What are the 1 and 2 qubit gate fidelities? Yeah. Most importantly, what's the main drawback of your system? The spec that's the worst, the one you most need to improve. What prevents you from having a scalable quantum computer right now? And are you going to tell me, or will you make me score Appendix 3.B in your paper, or worse yet, ask one of your competitors? I confess that the answers to the above questions are hard to summarize in a single number, unless you like concatenated binary encodings of them or something. But they can ineffably be ineffably combined to produce a progress metric that one of my postdocs suggested calling quantum Scottness, and which roughly equals to the number of expressions of wide-eyed surprise minus the number of groans. Okay, I think we can leave it here. Quantum volume seems like an interesting idea. It's a bit awkward in a couple of spots. And it's definitely stupid to use it as a measure of power in terms of that's my most powerful computer. I think that is something I agree with. So, okay, so that's kind of a like maybe here, but not a retweet. As in, like, sure, a simulator is a quantum computer as well, right? So this is not the most powerful quantum computer. It does, I think, as Scott puts it, like the moving away from using qubits as a single measure kind of feels like it makes sense, but it's like, I don't know. I don't even know whether it was worth the video, but I feel now a bit better because I didn't, even in this paper, I didn't really go and do the stuff with the quantum volume. So here it's introduced quantum volume and KQ. I don't know what KQ is. So what was that last mention? We found that the Ku-1 solution using C works well on quantum volume 8 and very similarly on quantum volume 16. The K1/4 solution using 0 and 4 qubits works, although not well on qubit 8. It performs much better, but still with limited effectiveness on qubit 16. I wouldn't say that, honestly. It works better on qubit 16. Why? How? Okay, better, as in like slightly better, but I don't think that is enough to call it slightly better. How would you even say that? The circuit is one of the largest KQ values reported to have been run successfully on a solid-state quantum computer to date. What is KQ, though? KQ is a measure of the capabilities of the machine independent of the algorithm. In 2003, Steen proposed a similar measure focusing on the algorithm's needs and on error correction for an algorithm using Q qubits and requiring K time steps. But that's okay, so that's just with times depth. The space-time product, KQ, is a guideline to the required error rate, which should be below 1 divided by K times Q. Interesting. Okay. So the gate fidelities are an interesting topic as well. It's the KL, or what is the KL? The KL divergence of the data relative to the expected probability distribution from pure state simulation compares favorably to that of a uniform distribution. What is KL divergence? KL divergence. It's a measure of how one probability distribution is different from a second. Okay. So I guess that's okay. How much something is different from the simulated probability distribution. I guess that's what the paper is using. But this is a little bit better. Mixed state values. Okay. As you can see, difficult is possible using current processes. For this particular problem, differences in the decoherence characteristics of the two processes result in the off-answer elements of this proposition decay more rapidly than the correct answer, resulting in an unexpectedly small decrease in overall success probability in the processor with a smaller QB. However, we expect that in more general cases, success probability will more closely track the KL divergence. Okay. KL divergence. Here for more convenient evaluation, we show the KL divergence. If you use a better value for them, it would suggest that the circuit is small enough for both processes. But how is it calculated? How do they calculate the KL divergence of 3 qubits? Subdivided Grover outputs. The KL divergence of the data. They are using these to compare with the ideal Grover's result. Compares from pure state simulation, compares favorably to that of the uniform distribution with all output values having equal probability. So it would be expected. Okay. With high noise levels, showing that quantum algorithms performs well. Uniform distribution with all output values having equal probability. So they're using this to compare the distribution from Pearson. It compares favorably to that of a uniform distribution. Figure 16. What is figure 16? Is this figure 16? Yeah. Uniform random output. Quantum algorithm performs well with all output values having equal probability, showing that quantum algorithm performs well, although the overall quality of Valencia is superior to Orense. Two output values, 0, 1, and 1, 0, 1, are more heavily weighted, giving a slightly worse KL divergence. 0, 1, and 1, 0, 1. 0, 1, 1, and 1, 0, 1. Yeah. And 1, 1, 0 as well. Okay. Okay. Whatever. So I think this basically clears out the stuff. I don't feel like I need to dig into this more, all honestly, even for the paper here. Okay, maybe also the fidelity. Gate fidelity. How is this calculated? Gate fidelity of Aristotle gates on realizes light blue points are the gate fidelity on IBM. I guess light fidelity is just it's related to the actual error rates, right? Are the gate fidelity on IBM equivalences? Light blue points are the gate fidelity on Orense of a QB8 and Valencia QB16 for each gate type. We tested all possible mappings to the processor topology, collecting the results of 8,192 shots for each pattern, the top and bottom bar, the maximum minimum values and experimental results. Okay, so you can see in QV16, right? In Valencia, the fidelity is much higher. Here's a big difference. But still, that doesn't have such a big influence in the final results, all honestly. While this initially appears as far as the dramatic reduction in required fidelity makes it a good trade-off for small problems, as shown by experimental results demonstrating effective amplitude amplification for 4-qubit search problems. I don't know. This whole thing here it seems to work really, but as I don't have access to Valencia, and Orense didn't seem to work well. I'll have to another take on this. Really, I feel because to Orense I did have access. Do I? I think I do have access. Yeah. So I should get similar results. Yeah. KL divergence. Okay, cool. But I solved also a couple of stuff in here, so I'm happy for that as well. Cool. But that was probably an unnecessary long video about where I started with the quantum volume stuff, and I just ended up losing myself with other things. But anyway, yeah, good. Perfect.